Have you ever wondered why we minimize the squared error? Or why we use regularization? You have come to the right place. In this video, we're going to explore the hidden connections between Bayes' theorem, loss functions, and regularization. We'll start with an intuitive visual breakdown of the concepts to make the math behind them crystal clear. Then, we'll dive into the core fundamentals and step by step derive maximum likelihood and maximum posterior solutions for regression. In the end, we'll tie everything together with a graphical demonstration of regularization. Let's head right into regression using a maximum likelihood approach. As always, we get noisy data sampled from some arbitrary function. In contrast to the standard linear regression procedure, we now assume that the data is distributed around the true function according to some probability density function. This makes it possible to assign a probability density to each sample. In this case, it is a Gaussian. The optimization task then becomes to find a function which accumulates the highest probabilities along its path. This is the concept that we will write down in a mathematical way next. The mathematical framework is nearly the same as in standard linear regression. We have a function model y that is a function over x parameterized by the weights w. The task is to determine the weights such that they describe the measured data y tilde well. We now additionally make the assumption that the additive noise is distributed according to a normal distribution with zero mean and some variance sigma epsilon. The noise term is IID, which stands for independently and identically distributed. This assumption will be explained later, when we go over the statistical preliminaries that are necessary for the derivation. However, we will not go much into detail about how to derive an optimal solution for the weights in this video. But if you are interested in how to solve this problem analytically, check out my video about the derivation for the pseudo-inverse solution of the linear least squares problem for regression. Continuing with the maximum likelihood approach, we can rearrange the equation above for epsilon and notice that the difference between the measured samples and the function that we want to fit have the same distribution as the additive noise samples. These terms are often also called the residuals, since they describe the difference between the measurements and the function that we fit. Interpreting this in a probabilistic way, this means that, on average, the errors between the function that we fit and the measurements will be zero. This, of course, only holds over all possible samples and not for a single one. This probability density function becomes the likelihood of our measurements. It can also be written down explicitly, since we assumed a Gaussian noise distribution. By plugging in the mean and the variance of this distribution, we get. This is the function to be optimized as seen in the graphical explanation. Before we continue our optimization procedure, however, I want to cover some mathematical and probabilistic fundamentals such that you can follow the next steps more easily. First of all, we need the chain rule of probabilities. The probability of two events A1 and A2 is given by the probability of the first event A1 times the probability of the second event A2 given the first one. We can easily extend this for three probabilities by extending the chain. We start at the probability for the first event and continue with the second, given the first, and then the third, given the first two events. As you can imagine, this chain can continue on forever. If we assume that the events are independent from each other, and the probability of a following event does not depend on the events before, this term can be simplified drastically to the product of the individual probabilities. In the case of our noise, this holds since we use the independence assumption from the IID property. Identically distributed in this case means that the distribution of the noise also does not change over time. Additionally, we need some properties of the logarithm for the derivation of the maximum likelihood estimator. It is a strictly monotonically increasing function, which means that if you increase x, the value of y will also increase. This property is very nice because if you apply the logarithm onto a function f of x, the position of the extrema, in this case the maximum of the function, remains the same. Another property of the logarithm is that the logarithm of a product can be rewritten as the sum of the logarithms of the individual terms of the product. Again, this can be generalized to an arbitrary number of terms in the product, which gives us the sum over the individual logarithm functions. With these two properties, we can now continue our derivation of the maximum likelihood estimator. Remember, we have some measurement data y tilde and a model dependent on x, parameterized by w, which we want to determine. In this notation, we collected all measurements and corresponding x values into a single set. The maximization problem can be interpreted as follows. We want to find the parameters for our model such that the likelihood to have measured the available data is maximized. For this, we split up the y tilde into separate samples to consider their probabilities. The same is done for the x values that belong to the points on the y-axis. From our model assumptions, we know two things. First of all, we know from our model function that a single point on the y-axis is fully described by its corresponding value on the x-axis, which means that we can drop the dependency of all other x values besides the one that belongs to the current y value. This makes it possible to split up this joint probability into the product of the individual probabilities as shown earlier. From the IID assumption of the noise, we also know that the values of y tilde are uncorrelated over time, which means that we can also remove these terms. Finally, this makes it possible to write down the probability for the whole dataset as this product over the individual likelihoods. Plugging this result into the maximum likelihood maximization problem from above gives us the following. Then, we can utilize the logarithm trick shown before and transform the product into a sum without changing the location of the maximum of the overall function. This transformation step is crucial for the next part. Up until now, we only considered general likelihoods, but from the initial model assumptions we know that the likelihood for the measurements was distributed according to a Gaussian. We can insert the Gaussian distribution into a derived likelihood. From the product rule of logarithms, we know that the product of the individual terms can be split up into a sum. The first part does not depend on the index n anymore and can be taken out of this sum. This constant term in front can be disregarded, as it does not change the optimization problem. We can also change the maximization to a minimization to remove the minus sign. The constant term is also disregarded, since it is also not relevant for the location of the minimum. What we obtain here is now the square error function that should be minimized. From linear least squares we know that a closed analytical form solution is available. Now, however, we know why we chose the square error function for that optimization problem and what makes it a good choice. This concludes the derivation for the maximum likelihood cost function. Using it to fit data might work, but often it is not enough to get satisfying fits for experimental data. I will explain the reasons for that in the next parts, and also show how to extend our cost function to improve the obtained results. This is where regularization comes into play. In this example, we again have some noisy data which we want to fit a function onto. The two model functions that we compare are a polynomial of third order and one of ninth order. Of course, the more higher order model is able to fit more complex functions and accurately pass through all the data samples, but is that what we always want? With the simpler model, we would get a result that looks something like this. The overall trend of the data is described, but not all points are perfectly hit by the fitted function. You might think that increasing the complexity of the model could help, but let's see what happens when we fit the ninth order polynomial. You can see that the data samples are hit better, but there are now oscillations and huge peaks in y. This is also called overfitting, where the function that is fit matches the data too closely, which results in large deviations to the underlying data, where there are no available samples, which in this case would be after minus n plus 1 on the x-axis. You can observe that the weight parameters of the fitted functions also increase for higher orders. This shows that if you want to fit a more simpler function, you want functions that are small in their parameters, to avoid fluctuations in y for small changes on x. Now that you know where our motivation for smaller weights comes from, I want to explain how this can be incorporated into our statistical framework. The idea for regularization is to include prior knowledge about the weights into the optimization problem. When you hear about priors in probability theory, a very famous theorem should come into your mind, the Bayesian theorem. It allows us to formulate conditional probabilities. In this case, we have the probability of A given B, which is the same as the probability of B given A, times the probability of A and divided by the probability of B. In most cases, it is enough to consider only the numerator and look at the function which is proportional to the conditional probability. We can apply the Bayesian theorem to our regression model in the following way. The model parameters become random variables, and we want to find the ones with the highest probability given the measurements and our model. This is also called the posterior probability, and according to Bayes' theorem is proportional to the measurement likelihood we had earlier, multiplied with the prior on the weights. For the maximum a posterior estimation, we now optimize with respect to this probability instead of the likelihood function that we had previously. In this case, we are able to work with this proportionality since the denominator is a constant that does not change the maximum. For the solution of this maximum posterior estimate, we again make use of the logarithm trick to split the posterior up into the logarithm of two sums. Then we maximize with respect to our model parameters w, which leads us to the maximum likelihood solution from before, plus an additional term which depends on the chosen prior probability. In machine learning, this sum is often denoted as the sum of two error functions, one which describes how well the model fits our data and comes from the maximum likelihood solution. The other one is the regularization error, which depends on the weights and their prior probability. To weigh one or the other more, a regularization term lambda is introduced. When lambda is small, deviations from the data are penalized more, while for larger values, the prior becomes more important. Now that we know how to incorporate prior knowledge about the weights into our model, we can take a look at specific prior distributions. For the first prior, we choose a constant prior, which means that all weights are equally likely. The logarithm of a constant is again a constant, which means that this term will not affect our maximization procedure and can be disregarded. To make the connection to linear least squares regression, we can say that the pseudo-inverse solution solves the linear maximum a posterior problem with a constant prior on the weights. For the next prior, we take a look at the Gaussian distribution around 0. This means that the probability for the weights is the highest around 0, so lower weights are favored. By applying the logarithm to the Gaussian distribution, we can see that the result is a quadratic term in the weights. This means that deviations from 0 are penalized quadratically when moving to larger weights. In machine learning, this regularization is often also called rich or L2 regularization. The third prior probability we will take a look at is a Laplacian prior. It is similar to the Gaussian one, but uses the absolute value instead of the quadratic form. By performing the same steps as before, using the logarithm of the probability, we will see that we obtain the Lasso regularization error, which uses the L1 norm of the weights. Finally, I will visually explain what happens when we add an additional regularization term on top of the regression problem. In this example, we have a likelihood function which is exponentially decreasing for large weights. This is not ideal, since increasing the weights will always lead to a lower error for the fit and will most likely introduce overfitting issues, as we have seen earlier. To avoid this, we introduce a rich regularization term on the weights. Now, instead of finding the minimum of the likelihood, we optimize with respect to the overall cost function, which is the sum of error from the likelihood and the prior. This leads to weights that are much closer to the origin and suffer less from overfitting issues. We can compare this method to the lasso approach. There, the deviations from the origin are weighted linearly and not quadratically, as in the rich regularization. This means that larger weights are not penalized as much, which results in a minimum of the overall function that is closer to the right. What is interesting to note is that the minimum always appears at the location of the weights where both functions hit each other. If you want to learn more about the mathematics behind machine learning, check out my playlist, which covers the fundamental principles step by step. It includes the derivations, but also practical computation examples and programming applications. Thanks for watching.